And probably the most important use of the derivatives for inverse trig functions is actually in integrating algebraic functions for which a u substitution just really won't work. Could you imagine, look at this right here, trying to do a u substitution on this. If this is the logical u, but then you're going to end up with an x in du. du is going to be, x dx, or du over 2 is going to be x dx. So that's not going to work. So look at this, and this is actually inverse sine. You can see that this function right here is the same as the derivative of inverse sine of x. So obviously, the antiderivative is going to be inverse sine of x plus c. So the solution to this will actually be inverse sine, like I said, of x plus c. Now, notice that the derivative of inverse cosine of x is negative 1 over this, which is a negative of this. So I could write this also as a negative of cosine inverse of x plus c. It's the negative because I don't have a negative here. If in fact this integrand was negative, that would match inverse cosine, so I would not need this negative. However, either way, we don't really go that route. If I had this integral, if I had the integral of negative 1 over the square root of 1 minus x squared dx, and you immediately recognize that as inverse cosine of x, or the derivative of inverse cosine of x. So the antiderivative is inverse cosine of x. We wouldn't write it that way. Rather, we'd write it as the negative of inverse sine of x plus c. It would not be wrong to say that this solution is inverse cosine of x plus c, because these two are equivalent. Rather, by convention, this is really the form that we typically put it in. Very seldom do we use that form. But like I said, they are in fact equivalent. So let's walk through a theorem that gives us a method of actually working out these. What we've been doing is we've worked with these where a is 1. 1 squared is 1. If this was a 1, you would immediately recognize this as being sine inverse. But it's a instead, so a could be any positive real number. So the antiderivative for this is actually going to be sine inverse, like you'd expect, but it's not going to be sine inverse of x. It's going to be sine inverse of x over a, and then of course plus c. Here, this looks like inverse tangent, and it is. Normally, we'd see this with 1 over 1 plus x squared. So you see, well, the antiderivative is inverse tangent of x. But we need to account for this a because it's not a 1. It is going to be, it is going to be inverse tangent, that's true. But it's going to be inverse tangent of x over a, just like we did here, and the whole thing will be divided by a plus c. Now you can actually verify these by simply taking derivatives, which we'll do one of them in a few minutes. This looks like, of course, inverse secant, and it is. So it's inverse secant, but it's going to be of x over a, and again I'll divide by a plus c. So this is kind of like a roadmap when you see you need to take an integral of functions of this form, how you can apply the inverse trigonometric functions to them. So let's go ahead and prove this one. Let's prove this right here is the same as this. And I want to take the derivative of it, and when I do, I should get this back. So if I take that derivative, I'm going to have 1 over a sitting here, times the derivative of arctangent of x over a. Well, derivative of arctan is going to be 1 over 1 plus x over a squared. Now, this is a function g of x, so I need, by the chain rule, I need the derivative of this, and the derivative of this is going to be 1 over a. Obviously, I'm taking the derivative with respect to x, so all of this will be multiplied by 1 over a. Okay, so now if I combine these, I end up with 1 over a squared times 1 over 1 plus x squared over a squared. And if I distribute the a squared, I have an a squared here, and it'll cancel down here. So I get 1 over a squared plus x squared, which is exactly what we were supposed to get. And you can actually verify this with each of these. It'd actually be a good exercise for you to do. Take the derivative of this and the derivative of this and make sure you come back to here and here.